time. So we're going to go ahead and get started. And people who aren't here on time can watch the video. So, hey, guys, we're getting started. Quiet down. All right, so what did everyone think of the homework? Hard? Yeah, this was a hard one this week. So just let's walk through sort of from the first couple of steps to the harder questions that people were kind of having some problems with. So the first question I asked was, say, okay, we'll give you a starting word list. Here's the words in the word list. There's 8 of them. And here's a string. And the first thing I asked is just some basic information of, if you take this word list and build a tree from it, what is that tree going to look like? So I told you last week how to build a tree. And so we're going to start with a root node. And then we'll serially insert words into our tree. So we'll start with the first word. We'll go down to A. And then that's the end of our word. So we'll end with a terminator node. And I'll mark that with a star. Our second word is A. We've already got an A in the first position. Then we've got another A and a C and a terminator. Then we've got A, C, B, and a terminator. And then we can do the rest of them: B, A, B, B, C, and B, C. Oh, sorry. B, C. There we go. And then we've got the last 2 words, which are C, A, B, A, and C, A, B. Okay, so this is the tree that we build on this word list. So the first question I asked should have been really simple. Practically everybody got it. And the first question was, how many terminator nodes are in this tree? And so we've got 1 terminator node for each word in our word list. So we've got 1, 2, 3, 4, 5, 6, 7, 8 terminators for 8 words in our word list. So that should be straightforward. And then the children of the root node are A, B, and C. Those are all of the possible first characters, which are A, B, and C, in our word list. And so we'll use this tree that we've built to go on and answer the rest of the questions. Okay, so part B is basically implementing what I just did here on the board. It says, take a root node of your tree and a word from the word list and add that word into the tree. And so you're just going to start with the root node, look at the first character. If the first character is a child of that node, we add it, or we move there. If it's not, we add it, and then we move there, and then we iterate using that new node as our new root and working on the suffix of the remaining word. Okay? And again, most everybody did just fine with this part. Part C is where people started struggling. So let's talk about part C. Part C said, let's take S, and we want to figure out if each suffix of S can be constructed from words in our word list. So the suffixes of S, the smallest one is just C, the next one is BC, and then BBC, and then so on until the last one is the whole length of S. So what I asked you to do is use a dynamic programming approach, where we're going to construct an array where each index marks one of the suffixes of S. So S has length 8. So we've got 8 spots here. So this last position is working with the suffix C. And so we can use our tree to check and see if we can make C from words in our word list. We started our root. We walked down to the first character, which is C. C doesn't have a terminator, so it's not a word in our word list. So this gets filled in as false. You can't make it from words, from these words. The next one is BC. So we start at the root, we walk down to B, and then we walk down to C, and then there's a terminator. So BC is a word in our list. We mark that as true. Same thing for the next one, which is BBC. Now for the next one, our suffix that we're trying to match is A, B, B, C. So if we start at our root and we go down to A, we can match the first character. The second character, there is no B here. We can't match it, so we can't keep going on. But we can split it right there. There's a terminator. So we can split it at A, and then this suffix can be composed of words in our list if and only if this suffix BBC is. And we can check that because we just filled it in our dynamic programming array. So we can say, okay, A is a terminator, we can split it here, and this can be made, BBC is a word in our list, so A, BBC can be split into words in our list. And then we'll go on to the next one, which is AA, BBC. And we get the same method where we split it here, and then we go and look up ABBC right here, say that's true, so this one must be true. And you can follow this chain of reasoning all the way down, and you fill in all of the rest of the array with trues. And you can obviously do this just by inspection for such a short word list. So S itself can be split up into A plus C, A, B plus BC. So that's a valid splitting of S. And that's what's marked here with the true. But for longer strings, for larger word lists, it's going to be hard to do that by inspection, and I want you to work through sort of the dynamic programming method to solving this by filling in this array backwards. Okay. So that was part C, and again, some people had some trouble with that, but most folks did okay. Part D was hard, and I know a lot of people had a hard time with it. So let's walk through sort of in detail how you might want to solve that. So for part D, I changed the word S. So I said, okay, instead of having that string, we're going to let S equal A, B, 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 C, B, B, C. So this can't be split into words in our list. So what I asked for was how many changes do we have to make to characters in S so that we can split it up into words in our word list. And I said that you can do this using the same dynamic programming approach that I described in C, except instead of storing here Booleans that tell us whether or not it's possible, we store integers that tell us how many changes we have to make for each suffix. So we'll start off with the last character here. So the last suffix, this last position in the array, is asking how many changes do we have to make to the string C in order for it to be represented by strings in our word list. So we've got three different options. We're starting off at the root of our tree. So we start off with our string C. We've got three options. We can change it. Actually, let's try swap to A. We can swap it to B, or we can match to C. Because those are the three options that give us words in our word list. If we change it, if we keep it at C, we're done. We can't do anything else. There's no terminator here, so this is not a viable option. If we swap it to B, again, we're out of characters. There's no terminator here. This is not a viable option. If we swap it to A, now we can terminate it. So we can change it to A, we can finish it, and now this is a valid match. And we had to do one swap from that C to an A, so we fill in a 1 in that position. All right, that's the simple one. Let's look at the next one. The next one is BC. So this is the suffix BC. We can start off by just looking for it as a word in here. So we go BC, that terminates. BC is a word, so we don't have to make any changes for that to be composable. Same thing for the next one, which is BC. That's also a word in our tree, so that gets us 0. So let's look at the next one, which is CBBC. Let's suppose we write a function, we'll call it f, of some string, CBBC, and the root of our tree there. And we write that so that this gives us the correct result. So that gives us the count of swaps that we need to make in order for that to be in our list. We can use that recursively to solve the problem. So again, we've got 3 different options. We can swap to A, the first character to A. We can swap the first character to B, or we can match that first character to C. So let's look at the first one. Again, we know that the answer isn't 0 because CBBC is not a word in our list. So we're expecting some positive number. So if we swap it to A, that initial swap costs 1 change. But then we need to somehow match BBC. So there are 2 different options. A has a terminator, so we can split it there. And we can say, OK, it's A1 plus, we can run this function on this shorter string with the root. And in fact, we don't actually explicitly need to run this function because we can go and look up in our dynamic programming array that that answer is 0. So if we swap to A, we can terminate at A, and then we can match BBC. So this takes us 1 swap. In fact, that's optimal. We can't do it in less than 1 because CBBC doesn't match. So we're done. We don't have to evaluate the rest of the tree. So let's look at, so we fill this in with a 1. Let's look at BC, BBC. Oops. And again, we've got a couple of different options here. We can match, we can swap, or we can match to B, or we can swap to A or C. I'm not going to go through this one in detail because it should be apparent that you can just get that with 0. Same one with this one. So let's go into this guy, B, 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 C, B, B, C. So we're going to start off with that first character. And we've got a couple options. We can swap it to A. We can match it to B. Or we can swap it to C. Let me start here just to show you a different path. So it should be clear that if we swap it to A, we can split it at A, BBC, BBC for 1. But there's another path to getting 1 change that I'm going to work on here. So suppose we match it to B. How can we calculate the total number of swaps recursively using this function? Well, the initial match cost us 0 swaps. So at 0 plus, we can call this function on f for the remainder of the suffix minus the first one that we've matched, BBC, BBC. But now we're not at the root anymore. We've moved down to this node. So we're at a subnode B. And so now we can start here. And now we've still got 3 options. So we're trying to figure out what to do with this second character now. And so we can swap it to A. We can match it to B. Or we can swap it to C. Suppose we choose to swap it to C. then that costs us 1 for the swap. Plus, if we go to C, that terminates it. So then it is f of C, B, B, C. And we're back to the root now, because we don't need to keep going down in the tree. And now that we're back to the root, we can go in and look it up in here. Did I make a mistake somewhere? Yes. Yes, I did. OK. Yeah. BC, BBC. BC, BBC. So now we can go ahead and look it up in the root, and this is 0. So the total cost it takes to swap C is 1. And so the total cost it takes total is 0 plus 1. So we can fill that in with 1. All right, so at each position, we've got to examine the different possibilities. And we will recurse on this function looking in at deeper nodes in the tree until we hit a terminator node, at which point we can go back and fill in from the dynamic programming array. OK? So that's the basic approach. I know it is difficult. A lot of you managed pretty well. I'm not going to go into great detail in the optional part because nobody actually did it. But the way to do the optional part, which was what you actually needed to solve the Google Code Jam problem, was to extend the dynamic programming array to a second dimension and calculate more different possibilities for it. OK, so that's the homework problem. Again, this was a hard problem. Congratulations to everybody who solved the whole thing correctly and everybody who made a good attempt at it. This week's problem will be easier, I promise. OK, so that is it for the homework. Let's talk about the lecture topic today. So this week I'm going to talk about binary numbers, binary mathematics, binary operations, and how to use them effectively and what they're useful for. So you can use binary operations, and you want to know about this not only because it's going to give you a better understanding of sort of how integer operations are handled directly by the computer, but also because being able to use binary representations of integers is a handy way to concisely represent system states or concisely represent subsets of items. And you can do a lot of very fast, very efficient manipulation of those using integers as not as numbers, but as sets of bits. OK, so has anybody not seen anything about binary numbers before? Anybody completely new to binary numbers? OK, good. So I can speed through this real fast. So basic ideas, we've got these place values that are powers of 2, 1, 2, 4, 8, 16. Maybe this is a 16-bit number. We fill in digits 1, 0, 1, 1, 0, sample 1. So this is an integer that is 16 plus 4 plus 2. So this is 22 in decimal. So each digit corresponds to a power of 2. Each digit is either on or off, 1 or 0, and the integer is the sum of all of the on digits. So most programming languages are going to use integers that have a fixed number of digits. Generally, you'll see 32-bit or 64-bit integers. In that case, the max int is 2 to the n minus 1. So if you have n total digits that you can store, the largest integer that you can store with 32 bits is where all 32 bits of those are on, and in that case, that number is going to be 2 to the n minus 1. So if you try and store a number that's larger than that, you'll obviously run into overflow errors where you're trying to use larger digits than you can actually work with in that system. So be careful with that. OK, so this is unsigned integers, where there's no sign. They're all positive. Signed integers are a little bit more complicated. So suppose we've got an 8-bit signed integer. So the place value starts at 128, to 16, 8, 4, 2, 1. So here's our place values, and maybe we've got the same, we're representing the same number. So 1, 0, 1, 1, 0. OK. So, and again, this is 16 plus 4 plus 2. So that's decimal 22. How can, now this in and of itself, with these particular place values, this represents an unsigned integer. Does anybody know how signed integers are represented in most standard programming languages? So one of these bits gets used as a sign bit. And the way that you do that is this highest order position, the 128, gets its sign changed. So now, if you've got a 1 in this position, instead of adding 128 to the total sum, you're going to subtract 128 from the total sum. Okay? This is called the 2's complement method of representing it. Don't ask why. It's historical blather for why it's called that. But it is called the 2's complement method. And this is the standard way that you'll see in pretty much every modern programming language. So if you're working in C, C++, Java, Python, they're all going to use this notation for it. And so how that would work is if we change this sign bit to a 1, but we don't change the rest of these, then now we have 22 minus 128. So what we're representing here is negative 106. So that means that the min-int here is negative 128. And that would be this sign bit on and all of the other bits off. But the max-int would be all of the other bits on, but the sign bit off. So that would be positive 127. So we've got total 255 possible numbers you can represent, 256 possible numbers you can represent, including 0. But now half of them are negative, half of them are positive. OK? So I'm not going to go into great detail about why the 2's complement system exists. But the reason that you should know about it, even if you don't have to know about how it works in detail, is that because negative integers work in this sort of subtractive manner, then doing binary operations on negative integers will not give you results that you may be expecting, because the remainder of the bits are not the same for the negative and positive numbers. Okay? So these same bits here represent negative 106 if the sign bit is on, but positive 22 if the sign bit is off. Okay? So you can't just switch the sign bit and expect to get the negative of whatever number you're working with. In general, it's best not to try and do binary stuff with negative numbers. But if you do need to do it, you should be careful of it because of how this system works. OK. So let's talk about some of the basic operations. So we've got several different binary bitwise operations that act on integers not as numbers, but as strings of binary digits. You generally want to use these operations mostly because they're really fast. Because they compiled a very concise machine code, they're usually even faster than just basic arithmetic operations. So adding, subtracting, multiplying, dividing are all going to be slower than using these binary operators. The notation varies a little bit from language to language, so you should double check in whatever you're writing in. But what I'll show you is pretty standard, so you should be able to compare this pretty well. And again, be careful because of the 2's complement system. Binary operations on negative numbers may not give you the results you're expecting. OK. That said, let's talk about the operations. AND. So the basic ones are AND, OR, XOR, and NOT. And you should be able to know what all of these do. So let's look at some sample inputs and see what that gives us. So this is 0, 1, 0, 1. So our place values here are 1, 2, 4, and 8. So this is 4 plus 2. This is decimal 5. This is 1 plus 2. This is decimal 3. So the end is usually notated by an ampersand. So 5 and 3, what the end says is, OK, we're going to compare the binary digits in each place value position. And if both of them are 1, they're 1 in the output. So we get 0 here because they're both 0, 0 here because only one of them is on, same thing here, and only in the last position are both of them on, and we get a 1 down here. So if you take 5 and 3, you're going to get decimal 1. All right? So that's the AND operation. And again, that is usually an ampersand is the command for that. OK. OR is usually notated by a vertical pipe. And OR, the bit is on in the output if it is on in at least one of the inputs. So here it's not on in either input, we get a 0. Here it's on in at least one, so we get a 1, and a 1, and a 1. So 5 or 3, we get 7. XOR, which is drawn with a caret, the output bit is on if and only if exactly one of the input bits is on. So here we've got 0 and 0. Both of them are off, so it's off. 1 and 0. One of them is on, but the other isn't, so it's on. Same thing here. Here, both of them are on, so it's actually off in the output. So 5 XOR 3 gives us 6. And in NOT, you need to be careful. Because what NOTs do is reverse every bit. So that acts on a single bit. So let me find a good, let me work with a larger number. So that works on a single integer, and it reverses the sign of every bit in the integer. So let's say take 1, 1, 0, 0. This is 12. And then there's an implicit sign bit here. So this would be place value 1, 2, 4, 8. And then this would be negative 16 here. And because it's a positive number, this sign bit is off. So if we take a NOT, which is drawn, usually done with a tilde, is the NOT function. So if we take a NOT of 12, we're going to flip all of these bits, including the sign bit. The sign bit gets flipped as well. So this is now sign 1, and then all of these bits get swapped. So it's sign 1, 0, 0, 1, 1. So the sign bit is negative 16, so we have negative 16 plus 3. So that is negative 13. A fun little trick for this, for these 2's complement signed integers, not n is equal to the negative of n plus 1. And we'll see how you can use that later. OK, so the other thing you can do that you'll see a lot are bit shifts. So if we have a number, say we've got 10, 1, 0, 1, 0. So we have a left and a right bit shift. So if we shift all of the bits to the left, so we push all these bits to the left, and then we bring in an extra 0 to fill in at the last bit. So you've got 0, 0, 1, 0, 1. What's the new number here? Ignore that negative right there. So if we left shift, this is 10, and we're going to left shift it, what's the new number?
Is it 20?
Yeah, 20, right? because now instead of having the 8 and 2-bit set, we've got the 16 and the 4-bit set. This is equivalent to multiplying your number by 2, right? And because, again, like I said, binary operators are faster than arithmetic operators, anytime you want to multiply or divide by a power of 2, you almost always want to use a bit shift operator instead. So this is a left bit shift. You can also do a right bit shift. So suppose we had 1, 0, 1, 0, 1 that we wanted to do a right shift on. This is 21. Then we lose whatever is in the right position. That just gets shuffled off into nothingness. But now we go 0, 1, 0, 1, and then we fill in from the left. So now we're back to 10. So a left bit shift is equivalent to multiplying by 2, but a right bit shift is equivalent to dividing by 2 while losing the most significant, or the least significant bit. Okay, so that's all the basic binary stuff. Hopefully that hasn't been too new to you. And you should be able to understand what we're going to do with it next. So, it's useful, yeah.
So when you shift bits, what happens to the sign?
That's a good question. And the answer is it depends on your programming language. If you're working in Java, there's actually 2 different bit shift operations. One which is 2 signs next to each other, and another one which is 3. And one of those, I forget which one works which way. You'd have to look up at the documentation. But one of those fills in zeros when you shift to the right. And the other one fills in whatever the sign bit was when you shift to the right. And so they're going to operate differently when you're working with negative numbers.
Triple right does the zeros and double right does the signs.
Okay.
So double right does the one that you would be more likely to expect from the shift.
Okay. Yeah, but again, be careful when you're working with negative numbers because that sign bit gets tricky. Okay.
Sorry, I don't know which one I said. Double zero does the one that you will be more likely to expect.
Okay. All right. So basic knowledge of how to do these binary operations is useful. You can speed up a lot of arithmetic operations. And they're useful for particular problems where they actually ask you questions about binary operations. But by far the most common way that you'll use these representations in the context of a programming challenge is going to be as a bit mask. So a bit mask is using the binary representation of an integer to represent a small vector of Booleans. So suppose we've got our maybe a 10-bit number, so 512. So here's our place values as powers of 2, 8, 4, 2, 1. So here's our place values, and then here is our digits. So 1, 0, 1, 1, 0, 0, 1, 1, 0, 0. Not going to make you add that up. That comes out to integer 716. So instead of interpreting this as an integer, suppose we have a list of 10 elements, and we want to keep track of which of those 10 elements we have in a particular subset. We can mark each of these bit positions with an element ID. So this is the 0th element. This will be the first element, second, third, fourth, and so on. So that now we can take an integer, use its binary representation, and now this integer, 716, also represents the subset of these elements from 0 to 9, that is 2, 3, 6, 7, and 9. Those are the bits that are set. So the bit 2 is set, bit 3 is set, bit 6 is set, bit 7, and bit 9. So those are the elements of our list of 10 that are actually included in the subset represented by a single integer. Okay? So this is a very memory compact, very efficient way to store a small list of Booleans. So you can use this a lot for subsets of elements. You can use this as maybe representing the state of a system, and then you can manipulate it very effectively. So let's talk about how to manipulate bit masks. So let's say we have a bit mask called S. Okay. So maybe we'll have a 6-bit number. S is 1, 0, 0, 0, 1, 0. OK, suppose we want to turn on a particular element in our bit mask. So here's our element IDs. How are we going to turn on, say, element J? So turn on element 3. We can do this with binary operations. So let's take 1 and left shift it 3 positions. So we start off with a number that looks like this. This is the binary representation of 1. And then we left shift it 3 places so that this 1 moves once, twice, moves 3 times. So we get this binary representation. OK? So that's 1 left shifted 3 places. Now if we do S or 1 left shifted 3 places, what are we going to get as an output? So we're taking an OR of this plus this. So we've got 0 here, 1 here, 0 here, 1 here, 0, 1. So this is our output string. It's identical to the input string, except now the element in the 3rd position is set. All right? So we can set an element in our bit mask with a series of binary operations. How would we turn off a particular element? Suppose that it starts on in position 3, and we want to turn off element 3. Well, we can do something very similar. Suppose we take 1 left shifted 3 places, do a NOT operation on it. Then we've got 1, 1, 0, 1, 1, 1. And now, what operation can we use to combine those 2 strings so that if this bit is on in the input, it will be off in the output? Which of these can we use? AND, right. So if we do AND, S and NOT, 1 left shift 3, then all of these, and anywhere there's a 1 here, we just read in from S. But this position will always be off. So we get 1, 0, 0, 0, 1, 0. That's our output. OK. We can similarly toggle an element. So if it's on, maybe we want to turn it off. If it's off, we want to turn it on by starting again with 1 left shifted to where we want to toggle it, and then doing an XOR. So now it's only going to be toggled if there's a 1 in this position. So there's a 1 there, there's a 1 there, so we'll turn it off. If it was off here, there's a 0 here, but there is a 1 here, so that is a 1 in the output of the XOR. So that toggles the position of whatever bits are set here. OK. So that's sort of basic manipulation. There's a couple other things you can do. So a couple other tricks that are nice to know. Suppose we want to identify the smallest bit that's set. So maybe we've got S equals, this is our 2's complement representation, 1, 0, 1, 0, 1, 0. So this is 42 with a bunch of leading zeros for the 2's complement system. If we take negative S, we switch our sign bit, and all of the other bits here are set. Good. And we swap all of the bits except the last ones. So 0, 1, 1, 0. That is negative 42. And if you're not convinced that that's negative 42, remember that if we take the not of a number, so not n is the negative of n plus 1. right? So negative n minus 1. So if we take not n plus 1, that's negative n. So if we reverse the sign of all of these, 0, 1, and then add 1, we add 1 here, that carries over, we get this number. So if we take s and minus s and end them together, we get zeros all through here, except for right at this position. And that tells us where the least significant bit is set in S. There are similar tricks to look for the least significant on bit and the least significant off bit. You can look in the lecture notes for how that works. So let me walk through a real simple problem from the Google Code Jam, and then I'll let you go and work on the homework. So the problem that we're going to talk about here is called snapper chain. This is a real problem from the qualification round back in 2010. So the idea is you've got these devices that have inputs and outputs. They can take power and they can send power out. And they've got an on-off switch. So if they're on and powered, they will send power to the next one up. But if they're off or they're not powered, either one of them, they won't send power at all. And so the question is, we've got a chain of them that are n long. And the last one here is plugged into the wall socket. So this one is always powered. And the question is, we can change their state by, they're called snappers because every time we snap our fingers, any of them that are powered turn on or turn off. They toggle their on-off switch. All right, you guys are looking confused. So they toggle their on-off state. So the first snap, suppose we've got all of these. This one is, let me draw a line down here for power. So we've got a power coming in. They're all start off. But the first one is plugged into the wall, so it's powered. So when we when we snap our fingers once, any of them that are powered toggle their on-off state. So that means that this first one is powered, so it turns on. And now it is both powered and on, so it passes power on to the second one. Okay? And then if you snap your fingers again, any of them that are powered toggle their on-off state. So this one turns back off, and this one turns on. Now, this one isn't passing power along anymore because it isn't on anymore. So it switches. So it stops power. So only this one is on. So then we snap our fingers again. This one is powered. It turns back on. And now we've got up like this. OK, so that's the problem. How can we use binary numbers to solve that problem? Well, the obvious answer is we've got a whole list of digits or of snappers, each of which are either on or off and either powered or unpowered. So we can store those values as a binary number. So instead of storing them as on-off in a big list of Booleans, let's write them as digits. So we'll have two bit masks. One we'll call power, and one that we'll call switch. And so the initial state of power is that all of them are off except the first one. And the initial state of switch is that all of them are off. OK? So when we snap our fingers, we take all of the powered ones and we toggle the on-off state. What is that equivalent to doing in binary operations? Right? So what's the new switch position in binary form? So the new switch position, again, we're toggling the switches of any of them that are powered. So that's equivalent to taking the XOR of the power bit mask and the switch bit mask. So we want to toggle this position, so we XOR those together, and now we get a new switch output where this is on, but all of the rest of them are off. Okay? So that's our new switch position. And then now we know that this one is powered and this one is powered. So this is our new powered number. So every time we snap our fingers, we're going to do that same XOR operation. So we XOR again, and now this is off, this is on, and now our power. So here's our switch, here's our power. So this is after n equals 1, n equals 0. This is after n equals 1. This is after n equals 2. So at each position, our switch went from 0, 0, 0. It went from 0, 0, 1. It went to 1, 0. What's the next position of that switch after I snap my fingers again?
1
Tell me again.
1
What operation are we doing?
So it's going to be 1, 1?
Yes. 1, 1. And then the power is going to be 1, 1, 1, right? So we start off our switches at 0, then 1, then 1, 0, then 1, 1. What's the next position of that?
100?
Yes. And so what are we doing every time we snap our fingers? Adding 1 to this bit mask. That's all that we're doing, is we're incrementing this bit mask by 1 each time through a complicated series of binary operations. So now, suppose that after we want to know, after we've got a chain of n of them, and we've done some very large number of snaps of our fingers, how can we tell if this one out here is powered or not? Suppose we've done, 3,852 snaps. How do we tell if the fifth snapper is powered or not? Yeah.
Take the mode of that number and the number of bits. And if it's 0, I think.
Yeah. Yeah, so you take this number as a binary number, and you take the position you want to look at, and you look at the bit in that position in this number, and if it's on, it's powered, and if it's off, it's unpowered. Okay? So that's kind of the basic idea for this problem. The problem that I've given you in the homework is fairly similar. Same sort of idea, where you're going to be working with bit masks and binary numbers to try and solve it. So again, the problem this week is another CodeJam problem. It's called candy splitting. You can look up the homework on the class webpage or at the bottom of the lecture notes. And that's it. So go get to work. Joey, did you want to say anything about the regionals?
Yeah, tomorrow, all of you who have signed up for the regionals have received an email, but it's tomorrow 1:10 for those who've signed up. And if anyone wants to show up last minute, then show up before 1. Because we need to get, since we have 6 openings